Okay, we're good. So it's recording now. Let me share my screen. That would make sense. That would be something important to do. Screen.
So shall we start?
Sure, why not? I don't know. Up to you.
Everyone knows Nathan, and Nathan will give us a talk about equilibrium measure. So let's welcome Nathan.
Yeah. So you guys can see my screen now. I don't know how well it's this. Well, we probably should have checked this earlier. But I think
it's fine. We can cut the thing.
Okay. So the title of this talk is a survey of equilibrium in the plane. So
wait a second. It's a
frozen?
Yeah, it's frozen.
Okay. 1 second. Worst case scenario, I could do a board talk, yeah? Let me write that down. And my screen stopped sharing, so let me try that again. Share screen. Yeah, and if it messes up in the middle of the talk, let me know and I'll fix it. Okay. Now is it okay? Maybe? Or is it still frozen?
I didn't see any notes.
Yeah, I still see it frozen. Wild. So maybe we're doing a board talk. Yeah, Zoom has been doing kind of some weird stuff lately, yeah? Like when you gave your talk last time.
Yeah.
Let me try one more time, and if it doesn't work, then I'll switch to the board. But try this, start broadcast. Okay, I think you can see that. Probably you can see that. It always freezes right there. So it's still frozen?
Yeah.
Board talk. Let me try something. So this is going to be interesting. It might be too low. How much of the board can you guys see?
Then you have to stop the screen.
Yeah, okay, one second. Let me stop that. Okay, so I guess board talk it is. I also have notes written, but probably would have been smarter to write them on my iPad or something, so I'll kind of just go off of this. And I'll try to draw big so you can actually see things. And let me figure out where I can actually stop drawing. So yeah, but I'll also figure this out later, because I don't know why. Maybe it's just an internet thing. I don't know if it's a Zoom thing or an internet thing, but you had the same problem, so I guess we'll have to figure it out. So anyways, that first board talk we've seen in a while, yeah. So can everyone see okay? If I'm writing too small, let me know. Or if it's too dark, I can't really do much about that, but if I can turn this backlight, it's a little brighter. And I think probably around, I can't go all the way over to here, yeah? Maybe here's where it is. So that's the board spacing out, okay. So anyways, what did I say I was talking about? Equilibrium? Yeah, so I said I was talking about a survey of equilibrium in the plane, blah, blah, blah. So just to mention before I start talking, a few applications of equilibrium, because it's seeming, well, I'm going to be talking about equilibrium as in electrostatics kind of things. Electrostatics is like a 19th century subject. So really the first question anyone should be asking is, why do we still care about electrostatics? Why is it important? Is it important? Should I even care? I mean, it's sort of interesting from the perspective of, if you're like physics 2, you're learning about electrostatics, maybe it's interesting. And you're just interested in electrostatics, maybe it's interesting. But are there actual applications? And the answer is actually, surprisingly, there are a lot more than you might initially think. So I'll just kind of list some of the applications on the board. One application is asymptotics. of ortho. When I turn around, can everyone still hear me, by the way? Yeah? Okay, good. Asymptotics of orthogonal polynomials. So that's one application, and in particular, asymptotics of their zeros. Am I writing big enough? Can people see that? I can't tell. My screen's really tiny, so it looks tiny to me, but I can write bigger if necessary. Okay, so other applications. So from random matrix theory, so for particular matrix ensembles, I'm not going to explain too much. Maybe I will at the end if we have time for applications. But so from random matrix theory, some of the applications include zero distributions of the eigenvalues of these random matrices of eigenvalues. And really, as a consequence of the first two, there's a third application, which is quantum gravity. 2D quantum gravity, I should say, but still quantum gravity. So it turns out that there are some very nice models of 2D quantum gravity that rely on random matrix theory, and as a consequence, rely on asymptotics with orthogonal. And so there are some nice applications to quantum gravity, actually, and this was a big thing in the 90s. And one more application I'll mention because Fadong is here, is integrable systems. So certain integrable systems, the asymptotics of certain solutions to integrable systems are again described by solutions to certain equilibrium problems. So just some motivation for why we might talk about something like this. So now that we've kind of overviewed why we care, maybe I should talk about what actually equilibrium is, because I kind of offhandedly mentioned. Let me just check the comments. What I mean by this, but I think we could be more specific. So I'm going to erase because I have some space, but I want to use the rest of the space to actually draw pictures. So let's get rid of this. And let's talk about what equilibrium is. So the question, what is equilibrium? So what is equilibrium? So first we need to consider, well, the object that we're working with, which is going to be a distribution of charge in the plane. So I have, I'll give a few examples and then maybe I'll mention, well, exactly what we're talking about. So what is equilibrium first of all? So the things we'll be talking about are distributions of charge. Example number one of a distribution of charge. So distributions of charge. Example number one is going to be a collection of point charges. So point charges. And that's my picture for point charges. And each of them has charge, so they're in the plane. Each one is at position zi, so maybe this is z1, z2, z3, z4, so on and so forth. And each one has total charge qi. So a very concise way to describe this distribution of charge is via a measure, and the measure is going to be du of z, which is going to be sum I equals 1 to n qi delta of z minus zi. So what this says is that each charge, there is a charge of position gi, and its total charge is qi. Just some other examples that we have them. That was example one. Example two is going to be a line of charge or a wire of charge, or I couldn't think of a really good word to call it, but line of charge. You can think the charge is now sitting on a wire, which is flowing through some wire. And this would be given by a measure like this. So some density of the charge times the arc length measure. So maybe I might have like a piece of wire sitting in the plane, and it looks something like that. I don't know. Is the glare okay? I see the, I think it looks not too bad. So example three. So example three, I couldn't think of a good word to call it, so I called it a blob of charge. And all I mean by this is something that is supported on an area. So there's charge in here. Its density, say, is rho of z, dA of z, and I'll call this thing dB of z. So this is just 3 examples of the things we're going to be working with, which are going to be measures like this. So in order to describe equilibrium with these things, we need to talk about how the charges actually interact, and the charges interact via the 2D Coulomb force law, or the Coulomb potential. So via Coulomb law. So the potential that one of the charges gives off at position z so potential is going to be proportional to log of the distance. So as an example, a point charge at position zi with charge qi has potential or gives off the potential qi maybe minus log distance. I just did proportional, doesn't matter. Log 1 over z minus zi. So this is a nice formula. So kind of something that's different if you're familiar with electrostatics in 3 dimensions or 4 dimensions or higher dimensions is that the interaction strength is no longer a power law. It's given by law, which is well, different, but it will make things interesting for us. So I guess that's all I want to say. So now I need to describe what equilibrium is. I still haven't done that. I think I need to erase. But maybe before I erase, I'll write one more formula. No, I'll write it once I'm done. So let's get rid of the pictures here. So just as a definition, the potential due to a distribution of charge, like this one, so potential, I'll denote by u of z. U stands for the distribution of charge, so it tells you where the charge sits. And it's given by, so u of z is going to be integral log 1 over z minus w d mu of w. And the integration is taken over wherever the charge is sitting, so the support of the measure. Okay, one more thing before I want to introduce before I introduce the concept of equilibrium, an external field. So I can also turn on an external electric field, which produces its own voltage. Its voltage will be given by some function v of z. So it's a complex value function. So you think maybe it's modulo z squared, maybe it's just z squared, so on and so forth. Maybe it's I don't know, sine of z, something weird. Could be anything. And it's some external electric field that I'm turning on that doesn't well, interacts with the charges. So what I mean by equilibrium. So by equilibrium, we will mean that the potential on the charges is constant. So in other words, if the potential is constant, the particle shouldn't move because it'll just sit in the constant potential space. Equivalently, this is saying that the sum of forces on any particular charge or at any particular point of the charge distribution is 0. So I've actually write this condition out. I think I'm going to put a 1/2 here. The 1/2 is a normalization. I'm actually double counting. I'll explain why in a second. So it means constant is equal to this. So this is just the statement that the potential, the net potential, which is the external field, the potential coming from the external field plus the potential coming from the actual charge distribution itself, is constant for z. I'm going to write support mu, some fancy terminology. All it means is that it's constant wherever the charges are sitting. So that's all this means. And of course, this integral is taken in what's called the principal value sense now, because, and I'll give a couple examples of what that means. So why is it in principal value sense? Well, we want to account, we want to neglect self-interactions. So, for example, this point charge sitting at Zi doesn't interact with itself. So what did I want to say here? So a couple examples of principal value sense, because why are we considering this in principal value sense? Well, this integral actually doesn't make sense if Z sits where U is not equal to 0. So if Z sits outside of the charge distribution, then this is perfectly well defined, there's no problem writing it. But of course, if it sits outside, then we have sort of a problem. So we have to deal with that. And we're doing out of time. Okay. So a few examples, then I'll call this something. So as an example, for a distribution of point charges, equilibrium will mean V of Zi plus some J not equal to I Qi log, sorry, I don't want to write log so high, 1/2 log 1 over Zi minus Zk is constant. So the principal value sense is the fact that I'm not summing over the J term, J equal to I term. Not included. This is because we don't account for self-interaction. So we assume that the charge doesn't interact with itself, which is an assumption that's necessary to make. And of course, there's something to note, there are n equations here. So I goes from 1 to n. So this is saying, this statement says that the potential at any point of the distribution, so in this case, we're looking at the point Zi. At any point where the charge is sitting, the potential is constant. So this is what this says, and I just said a name for this. This is called, so this condition is called the Frostman condition. Frostman condition. And we'll probably take a look at it later, because we will need to. So that's one sort of equilibrium that we'll be talking about. The other sort of equilibrium we'll be talking about is what's called constrained equilibrium. So I want to mention that too really quick. And I'll kind of compare and contrast the two in a second. So constrained equilibrium means that the charge is required to sit in some fixed region of space. Region, I'll call it K of space. And those of you that like words, K should be some compact set in the plane. And the charge can't leave this compact set. So you can imagine maybe I'm talking about a wire, and the charge should only be flowing within the wire, and it will somehow jump out of the wire. Or maybe I'm just talking about, maybe I have like a metal plate, and the charge is sitting in the metal plate, and it shouldn't leave that. So those are kind of two examples of constrained equilibrium, or why a constrained equilibrium might be mentioned. And for our purposes, so from here on out, we're going to consider distributions where all the charges have the same sign. So say minus sign or plus sign. So meaning behind this, we're considering a bunch of electrons. Maybe they'll even all have equal charge, for example. And then there would actually be a bunch of electrons. They all have the same sign, and these are the sorts of problems we'll be interested in. So these two classes, equilibrium in an external field and equilibrium constrained to some set. And I'll explain why both we should be able to picture that they have a solution. So all charges will have the same sign. So for lack of a better word, bunch of electrons. So the two problems we mentioned were one, I'll label them backwards actually because I'm going to label them in the order I'm going to address them. One, constrained equilibrium. So let's try to picture why this might have a solution, or why it should have a solution. So Of course, electrons want to repel. And so if I don't add the condition that they're constrained to sit on some set, then the electrons will just go fly off to infinity. They'll all repel each other and they'll all move away. And of course, then the problem won't have a solution. But if I require, say, they're fixed to some disk or something, then we can imagine, well, let's even try to work this out. So maybe I have a bunch of electrons inside, or maybe a blob of electrons, like that. And now I ask the question, I release the electrons, and they're required to sit somewhere on this disk. Where do they go? And well, the answer, at least intuitively, is clear enough. So first of all, the solution should be symmetric. So rotationally symmetric, because there's no really preferred direction here. And second, they want to be as far apart as possible. And so the obvious answer should be that they all go to the boundary and equidistribute on the boundary. All right. And we'll talk a little bit more about this case in a little bit. But first, now I want to mention the other kind of equilibrium that we're talking about, which was equilibrium in an external field. So suppose I don't impose the constraint that the electrons are required to sit in some fixed region of space. Well then, if they're just sitting in nothing, then of course they'll want to fly out to infinity. But maybe if I turn on a strong electric field at infinity, and I require that on, so the electric field confines. So it tries to keep the electrons close to, say, well, close together. Then maybe I can actually balance the Coulomb force. I drew a pretty picture. So the idea is to balance the external field. So I need to prove or choose an appropriate external field and balance it. This is supposed to be like a seesaw with the Coulomb force. And then I can hope that there is a solution to the equilibrium or to the equilibrium problem. And so we'll, the examples that I'll give later will all be examples where this actually does happen. We do have a nice balance. And so we'll get an interesting solution. So those are the kinds of problems that we're talking about. And maybe the two examples we'll end up addressing. Or the example I eventually want to get to, at least in two. So one, we're going to try to do it in general. So any given fixed compact, we'll try to come up with what the solution to the constrained equilibrium will look like. Where will the charges sit? That's the question we're going to try to answer there. In the second case, we can't be as general. So I'll try to address a few particular cases. And the one case that I really wanted to address that I think is interesting is what's called Wigner's symmetrical law. So I'll explain what that means really quick. Maybe I'll do it over here because I kind of had a room at the bottom over there. So let's get rid of some things. So Wigner's symmetrical law. So the law is going to be as follows. I say that the charges live on a straight wire. So here's the wire. I'll draw it. It's just going to be a linear line for us. And my external field, V of x, is just going to be quadratic. It's going to be x squared. So the potential, the external field, will look like, let's use green maybe. That. So this is V of x. So I turn on this electric field, which you can kind of imagine. So the particles want to repel, but this external field keeps them from repelling too hard, if you will. Can you guys see that? I don't know if the green is showing up. Looks okay. I see Fidong's thumb. So
okay. It's okay.
You can double click your picture, your camera, and it will bigger.
Oh, can I? Let me do that then. And all the comments on the way. Yeah, okay, I can see that then.
Mm-hmm.
So the idea is, if I try to solve equilibrium, or the equilibrium problem in this external field, I have to look at myself. Oh, yeah, I turned that off. So where does the charges sit? Well, they'll sit in some interval. So they won't go too far apart, but they won't come too close together. They'll sit in some interval. And what is the density of the electrons in an interval? Well, it ends up being just a semicircle. So that's something we're going to try to cover. We'll try to come to that result. And maybe do something a little bit more general if we have time. Oh, right on. So The next question is going to be about how to compute. And I think I can actually skip the minimization part. So our problem now is going to be, we're going to move on. So our problem is computing equilibrium measures. So essentially, that's the goal for a while. It's just to try to come up with some examples of equilibrium measures. So we kind of already did this in one case. Let me close this, and I can actually see what I'm pointing to. If the charges sit inside and I release them instead of some disk, then clearly, if they all have the same sign, this is what I equidistribute on the boundary. That was one example. Let's try to do that more generally. So the first case we're going to consider is going to be constrained equilibrium. So we want to try to construct generically where will the charges sit, or answer the question, where will the charges sit in a constrained equilibrium on some fixed blob or some fixed metal plate, say. So constrained equilibrium. So like I said, suppose I have, we'll kind of talk about this example a bit more. So suppose K for us, this region of space is going to be the disk. And we have total charge T naught to distribute. So we maybe do that in a different color. T naught, so I have total charge T naught to distribute. Well, we already talked about how it should uniformly distribute on the boundary of the circle. So the measure, equilibrium measure, which I'll denote by, well, for right now, d mu, but I might change to d lambda later. D mu of z in equilibrium will be T naught, and let's do the disk of radius, r, why not, over 2 pi r d theta on the boundary of the disk. So boundary of the disk of radius r. So that's our first example of an equilibrium distribution. And it was kind of nice and intuitive, but it's very special. Yeah, we can't claim that that will be true in any case. So, for example, if I did a box, or maybe my distribution or my metal plate looks like something a little bit less regular looking, like that. I don't know. Well, in that case, where will the charge sit? The glare is kind of bad. This one, it's kind of dark, but I think it works. So maybe K is this. Where does the charge sit? So the first thing I want to talk about, I'm not going to do hopefully any proofs. I'm trying to make this as intuitive as possible. So the first thing to kind of address is, well, can the charge sit on any of these inner boundaries? So if I put total charge T naught somewhere inside, and I release. So here's the charge maybe. I release it, where will it go? Can it sit on these inner boundaries, or does it have to go to the outer boundary? And well, the clearest thing that probably, or the thing that should probably make sense is that, well, the charge has to go to the outer boundary, because that makes it as far apart from the other charges as possible. So remember, all these charges have the same sign, they want to repel, and well, they're fixed on this set, so the farthest apart they can get is if they go and sit on the boundary. So I'll call that theorem 1, but really our proof is just a physical argument. So our theorem 1 is that given something like an n-connected domain, like this one, given an n-connected domain, equilibrium measure, and I'll write words, but then I'll explain what the words mean. The equilibrium measure is supported on the exterior boundary component. I should say bounded. Exterior boundary component. So i.e., if my domain looks like this, then all of the charge, if I release it from rest, will want to go somewhere on this piece of the boundary. So somewhere out here. And then it will sit on any of the inner boundary components. So the next kind of natural question, so now we know where the measure sits. We know it lives on the outer boundary component. And so probably we expect, so our expectation is going to be that the equilibrium measure should be described by well, some density on the boundary times the arc length measure. So I'll write dz modulus maybe, but ds might work better here. So the question now is, what is this density? So it should be clear, maybe not clear, but it should be a little bit clearer that probably the density isn't uniform. Why? Well, suppose I put, if it was uniform, probably the Coulomb interaction here would make them want to push farther apart because this piece of the boundary is kind of closer to the other electron. So probably we expect the density at on this piece of the boundary here to be lower than, say, the density on the boundary over here, where the charges are kind of more spread out from the other charges. So the piece of the boundary is kind of longer in some sense, or less far apart. It's kind of a vague explanation, but I think maybe from intuition's sake it makes sense. So here the electrons are actually closer together, so probably there will be less electrons here than there will be over here, because the boundary is closer together to itself. So the density should probably be smaller. So what should the density be, sort of the question. And the intuitive answer that I came up with, because I was trying to come up with a good intuitive way to think about this. And here's my answer, my intuition's answer. So the density should be proportional to the probability that a fixed particle electron, let's say, will leave through that segment of the boundary, that piece of the boundary. So the density of electrons, a good way to think about it is if I release all the electrons, they'll all go somewhere, and their density will be approximately proportional to the probability that it'll actually lead to that piece of the boundary. So for example, this piece of the boundary is bigger or more spread out, and so likely if I drop an electron here and I release it, it will go out to infinity, and it will leave through some piece of the boundary. So the idea is the probability that it's proportional to something like the probability that it comes to the boundary. And the only point that I can kind of pick uniformly from that is the point at infinity. And so what will actually be, this quantity actually has a name. This is called the harmonic measure. And it's actually the harmonic measure of something particular, so I'll write what it is. It's the harmonic measure omega of, all right, omega E.
Hi Nathan, sorry. Can you read again the what you wrote over there on the yeah, that one we can read it.
Yeah, sorry, I wrote kind of poorly.
Okay.
So because probably the electron will hit a piece of the boundary, so will leave through that piece of the boundary. So kind of the idea is if I drop an electron at infinity, let me draw.
Thank you.
Here's my domain. I drop an electron at infinity because it's really the only uniform place where I can kind of consider it coming to the boundary. I wasn't probably that it will hit the boundary at that point, and that's what the density is going to end up being. So the electron will come and pass the boundary at some point, and that would be the probability, or that would be the density of electrons, or the density of the equilibrium measure, because that's where it has to sit, so it will leave and go through that piece. So omega E is, in the picture I drew over here, is this blue domain. So it's the exterior of K, not including these inside pieces. So the connected component of infinity, if you will. So that's omega E. I'll write it in blue. I wrote it over here. So actually, the nice thing about this formulation of the density is that so the fact that we connected it to the harmonic measure is very useful because there are actually nice explicit formulas for the harmonic measure. And so, well, I'll write those now. They're actually in terms of what's called the Green's function of the domain. I want to leave that picture up, so maybe I can erase everything above. Yes, I'll get rid of this. I'll get rid of this. And I think I'm going to have trouble erasing this blue and this red because the markers are bad. But let me keep going. So what was I going to say? I'll just make the comment up here. Harmonic measure is computable in terms of the Green's function. Should Green be capitalized? It's a guy's name, but I think it should be capitalized. Green's function of the domain. Or of this the domain omega e. So this harmonic measure is actually written as dg omega e dn ds. And actually this was, so I'll explain what g is in just a second. So this is, I just want to write the answer. du of z. So this is our solution. This is actually the equilibrium measure for the constrained equilibrium problem we had posed earlier. And what do I want to say here? So I was going to tell you what the Green's function is, because that's a maybe unfamiliar concept to some of you. So the Green's function is just a solution to a particular derivative problem. It's a solution to this one. So it's a solution to this partial differential equation. Laplacian g omega e is equal to delta, in this case infinity. So there's a, I'll write it in the notation I was using earlier, delta of z minus infinity. Get that with a grain of salt. It means Dirac mass infinity and g omega e on the boundary, omega e, which is this green component here, is equal to 0. So this is the Green's function for that domain. We can give a better explanation, but I think for time's sake, for right now, I want to move on. And one more additional comment I want to add. There should be, appropriate normalization should be 1/2 pi. And if I want it to be a total mass T naught, so I have a total number of electrons or amount of electrons T naught, the total mass of the electrons is T naught, mass of the measure. And there should be a T naught here. So this is the harmonic measure for the constrained equilibrium problem that we posed in the beginning. And I'll give one more example, which we won't prove, but maybe it'll be clear as well. So an additional example, aside from the one that we already did for the circle, let's do the second minus L/2, L/2. This is K now. So the electrons are now defined to live on some segment. So from our intuition, and this example is supposed to show you that intuition, we need a little bit more than intuition to be able to show things. So the electrons are now confined to live on this interval. Here's minus L/2, L/2. And from intuition from before, we'd expect that since all the electrons want to repel, they'll probably all go to here and here, and maybe equally distribute there and there. But it turns out that the Coulomb interaction isn't strong enough to push them all to the boundary. Or it's so strong that putting them all on the boundary is just it's too much. If they all sit at a point, then the energy is actually greater than if they distribute somehow inside. How should they distribute inside? Well, they do distribute something like that. So it's actually this is the density of the electrons. So they're that dense. I don't think I drew that great. But the actual density of the electrons, I'll just write for you. d lambda, where I've been using d mu, so I'll keep using d mu. D mu of x is given by what's called the arc sine law. T naught over 2 pi, or is it just pi? Pi, sorry. T naught over pi, yeah, it should be pi. Dx over square root of L squared over 4 minus x squared. So this is what the density looks like. I did green again. Here's the density of the measure. And it looks something like that if I were to draw it. So for right now, I think that's all I want to say about equilibrium on a fixed compact set. So the constrained equilibrium problem. And now I want to move on to talk about equilibrium in an external field, which, well, we can't do so intuitively. We'll need some tools, but the tools will be just good complex analysis. So nothing more complicated than some good theorems from complex analysis. Very well, one of them maybe won't be so standard, but at least two of them are. So we're going to use Liouville's theorem. We're going to use Herrera's theorem. Yeah, I'll keep going. I don't know. I'll not run over. So at some point we may just stop. Fedong, did we find someone to speak next week? No, we'll talk about it later. So this may go into a part 2, but I won't unless someone wants to talk. So let's get rid of this, and then let's start something new, which is going to be equilibrium in an external field. Equilibrium in an external field. So again, this is the idea that we have some number of electrons, and now if we turn on, well, first of all, they'll want to repel, and if I turn on a strong enough external field, so some external electric field I turn on that confines the electrons, they'll live somewhere kind of close together, maybe in some blob. And the question will be, what blob is that, or what line segment is that? And because the problem is in general very hard, we're going to work with a couple explicit cases. So we'll need more than just our intuition, and we'll need to actually use a few theorems from complex analysis to even be able to say something in a particular case. So the particular case of interest for us right now, interest, is going to be the particles live on. So particles live on a wire. And they live in this external field V of x, which is a polynomial of even degree. So the external field here is a polynomial of even degree. And our goal is going to be to attempt to answer what the density of electrons should be if they live on a wire and they have this external field. So let me just draw a picture. Here is where the electrons sit on this wire, this R for us. And the external field they sit in is something, where did the green marker go? It's over here. Something polynomial. So it looks something maybe like, that could be V, for example. But we'll find that out. Okay, you can see that. We'll find that even this problem's maybe hard to answer in general. So we need some assumptions. Our first assumption is going to be that the charges live on a finite union of intervals. And this actually, the number of intervals is actually just n. So they'll live on n intervals if the external field is V to the n. And this sort of, at least intuitively, I think, is clear because where else could they be? So the external field is confining them, and maybe they sit here, and maybe the field is strong enough in the middle so that they don't live in this piece, but then maybe they live over here as well. So here maybe the electrons live here, and they live here. Maybe they don't live there because the field is strong enough or something. I don't know. So fact number one, we're going to take for granted that the support of the equilibrium measure will be a finite union of intervals. In other words, the electrons live on some union of intervals. Okay, so I wrote some words. We will use one of the first formulas that we wrote down plus some good old-fashioned complex analysis, that's cheaty, to determine what the equilibrium measure will look like. So how to actually determine what the density of electrons is on the support, so where they live. And we'll actually use a condition that we met at the very beginning, which I wrote down, and we didn't really talk about all that much, so it made it kind of weird that I even wrote it down. But we'll come back to it. So the thing that we talked about was the Frostman condition. So that's actually what that's gonna be the solution to our problem, kind of. So yeah, that's gonna be fun to erase. Okay, it's gone. Good enough. So the Frostman condition is what we're gonna use. It will be a very useful tool for us. And if you remember what it was, it said that anywhere where the charge sits, the potential should be constant. In other words, the sum of forces should be 0, and actually that's the formula we use. So it was plus 1/2 log 1 over z minus w, d mu w is constant. And actually the version of this that we'll want to use, because it's a little more easy to work with, and actually we can say some things about it, is going to be well, the condition that the sum of forces is 0. So all I need to do is differentiate the potential on both sides. So I differentiate this expression, I'll end up with the equation that sum of forces should be 0. And so I'll do that. V prime of z plus, and I'll multiply by 2 because I don't like that 1/2. The integral of u w over z minus w is equal to 0. So this is equivalently called the Frostman condition. And this thing, we're going to be minus this thing, so I'll write it as w minus z. Minus sign. I think I have signs off. I do already, so there should be a plus sign here. I need to check the derivative, but this should be the appropriate sign. And this thing I'll call the Cauchy transform of the measure. So it's called quote unquote Cauchy transform. Is equal to integral du over w minus z. So it's a useful quantity, I claim. And well, the fact that we know something about actually this density, and a little bit a nice theorem that we'll use from complex analysis, we'll actually be able to determine precisely what the support of the equilibrium measure is. So let me keep writing. So again, this thing is taken into principal value. Also, maybe just to note principal value, I'll draw a line through it. And the line means principal value sense. So again, it doesn't really make sense to just write this into because it's singular if z is in the support. Writing that, sorry, that's an important condition. I said it, I didn't write it. It only makes sense if we desingularize. We didn't take it in this principal value sense.
So here the measure is what measure? It's area measure or arc length measure?
It could be either. So in our case, actually, how I'm about to say this, since we know it's supported on a union of integrals, probably what will end up being is that d mu of z is going to be rho of z dz. And here dz is just dx. I'm not going to write modulus dz. So actually, that's kind of another assumption we're going to make that it's absolutely can use with respect to Lebesgue measure. But it's sort of an actual assumption because it's supposed to be a line density. It lives somewhere on a line, and so probably its density will look like some function, positive function, times the arc length measure, which is sensible. But in general, you're right. It could be, well, it could be anything. But in our case, it's this. So we're in luck. And because of this, actually, we're going to use a nice formula for complex analysis. Yeah. So because the measure takes this form, well, we're going to use a nice formula from complex analysis to be able to actually determine what rho is. I'm going to write the theorem here. So it's a beautiful theorem. And if you were here a year ago, I think, last summer, Fadon gave a nice talk on this formula. So I don't think I'm going to pronounce the first guy's name right, but I'm going to say it anyways. So Sokotsky, I think that was close. Plumel formula. And the formula actually gives you well, a way to recover the measure of something like this. So the theorem says this. Consider this integral. So I'll call it C mu again. Z is going to be integral d mu w over w minus z. Z is outside, and I'll write it, let's be more specific. Rho z, and z is outside the support of rho z dz. The Plumel formula gives you a formula for well, one, the density, and two, the principal value of the integral in terms of limiting boundary values of this integral. So the boundary values means, so maybe this is the support, 3 intervals. So the boundary values are the limit as z approaches from this side and this side. So I'll give 2 definitions. Let's call this the plus side and the minus side of the support. So C mu plus of z is going to be the limit as w goes to z from the plus side of C mu of z, and then C mu minus is the same thing but with minus sign. So approaching from this side. And the theorem says the following. It says that right over here, and I think I'll get up to the way so you can see. So C mu plus minus C mu minus is equal to 2 pi I times the density. I'll call this 1. And 2, the sum of the two, C mu plus C mu minus is equal to this principal value integral. For any z in the support. So let me get out of the way so you can see. I said some things. I think we're almost out of time, so I'll kind of speed up just a little bit. So these are the Plumel formula. The other formula we'll need, I'll just write. We won't give a proof of this. If you want to see a proof, ask Fadon. That kind of looks like a bar of integrals on a bar. I have your notes somewhere on that proof, but I don't remember how it went. So I'll have to go back and look. But we'll take this theorem as fact. Similar thing we need, which isn't so hard to derive, is that the Cauchy transform satisfies this condition as z goes to infinity. So where does this formula come from? So it's an expansion for C mu of z in the neighborhood of infinity. And where does it come from? It just comes from well, expanding w minus z as a series at infinity, and then just taking term by term integrating. So the first term you end up with just the mass of the measure with the minus sign for z, and the next term I don't care about for right now. It's something else. So we only need to know the leading term. So, right. Good. So the idea that I want to write down, and then I'll write a theorem that kills it for us. The idea is going to be in order to determine rho over z, all we need to know is the Cauchy transform of rho. Why is this sufficient? Well, the Plumel formula, or why it's sufficient. In order to compute the density, all I need to do is know the Cauchy transform, and then just take limits from above and below the support, and that will give me the density. So it's enough for us to just know what the Cauchy transform is, and then we can actually compute the density. And that's sort of going to be what RDA is, and the theorem that kills it for us, which I wanted to kind of give a sketch of, but I don't think we have time, so I'll skip it for right now. So suppose U is an equilibrium measure, in the external field, which was given at the beginning. V of x is x to the 2n plus lower order term, so it's a polynomial of degree 2n. Even degree again because it has to confine. And with total mass, so the total amount of charge we're distributing is T. Then there is a polynomial, P of z, which is of the form minus 4n T naught, z to the 2n minus 2, plus lower order terms, such that the Cauchy transform of mu squared plus, is it 2 v prime times the Cauchy transform minus that polynomial is equal to 0. Which seems like a dumb thing to write down. Why is that helpful at all? So that's our theorem. This is a theorem that I claim helps us a lot. Why is it so helpful? So it's helpful because, well, the above is quadratic in C mu. And so we can actually solve explicitly for what C mu is. C mu ends up being, C mu ends up being minus v prime of z by just using the quadratic formula, plus or minus the square root of, make sure I get this right, v prime squared plus p. So there's an explicit formula for the Cauchy transform, and if I actually take limits now, what I find out is rho of z is 1 over pi, the square root of minus what's inside here, so minus p minus v prime squared. So just using the Plumel formula, I'm able to determine the density. So something I didn't mention maybe, and if we had more time, I would actually go through the proof. And don't want to talk next week, maybe I will. But the reason that why I mentioned this formula and this theorem up here is because they're actually kind of instrumental in actually proving this thing. This is where some good complex analysis comes in. So if you're taking complex analysis now, or you want to try a good complex analysis problem, try to prove that theorem. It's something complicated. So given this formula, given that theorem, prove the theorem below. So actually we have an explicit formula for the density. I think the last thing I'll do is just show how, for the first example, that Cauchy transform actually, we end up with the semicircle law. So let me erase. So the example is semicircle law. So the potential for us is x squared, and the total mass, so the total charge we're allowed to distribute is T naught. And well, using this theorem, there's a polynomial of degree n minus 2, and here is just 2, or n is 1 for us. And so the polynomial itself is just a constant. So P of z is minus 4 T naught, and v prime for us is 2x. And so using this nice formula for the density, we find that the density is 2 over pi, square root of T naught minus x squared. So indeed, for this external field, let me draw the picture again. The charge is set on a wire. I turn the external field like this, so v of x squared. And the charges will distribute according to this semicircle law. So the radius of the circle is minus root T naught, root T naught. And the density of charges inside this semicircle. So I had a couple more comments I wanted to make, but for right now, I won't make anything because I'm out of time. So any questions from anyone? Let me sit down.
Nathan, I mean, you don't have to give 300 pages of potential theory in 1 hour.
Sure.
It's
well, I'll tell you the theorem that I wanted to get to.
But one thing is, like, for instance, you know, coming to the end, what are the conditions on the density? Because it would be nice if Sokhotsky-Plemel held for no matter what the density is, but that's just not true.
Yeah, so you need to have support like, well, first you need to have support of intervals, and you want a general
Well,
density.
right, but I mean, you know, how do we want it? How do we want Plemel-Sokhotsky to hold? Because, you know, you want to hold it at every point. The jump is the density.
Right.
Then
So the point of the support of the measure. In this case, since the support is just finite.
Well, that's obviously implies that you, at every point, the density should be well defined if it represents a jump of the potential, right?
Sure. Yeah.
Well, that, I mean, if the density to start with is an integrable function, that's already not holding water.
Stronger with the conditions. I agree. So
well,
we need
I know. I mean, Cauchy. I mean, before even potential theory, the kind of behavior of Cauchy integral, because for mathematics development, Cauchy integral was way more important than potential theory.
Yeah. So probably a good answer I could give you is that we need at least that the density is Holder continuous. We'll say.
Holder continuous is certainly sufficient. That's original Sokhotsky's.
But even that can be weakened.
Theorem, but it doesn't have to be. It actually can be arbitrary measure if you are still on the real line.
Yeah.
But then you have to change the statement. You have to sort of, it doesn't hold everywhere. It holds, of course, where it makes sense, where the measure has Radon-Nikodym, where the measure has Radon-Nikodym derivative with respect to arc length and or almost everywhere with respect to the measure. And those are, I mean, I'm not picky, but those are actually very deep results. Like in particular, generalization of Sokhotsky-Plemel, it's Privalov's dissertation from 1918. And the result is difficult and there is no royal proof to it. It's called Privalov's lemma. It's for arbitrary density.
Well, no, you talked about that, yeah? Or you wanted to at some point.
Well, yeah, when I teach complex topics and complex variables, I do talk about it. But it just, I mean, you know, it's important to, there are no theorems worthy of the name that hold with no assumptions.
Exactly.
For us, we might even assume that the density is smooth.
Right, and
so a comment I wanted to make to Fadon at least. So you kept asking why are we allowed to assume that the support is actually a finite unit of intervals? I actually found a good reference.
Why what?
Why are we allowed to assume that or how to prove that the support is actually finite unit of intervals? And why is it in intervals? So I had a paper reference for you, Fadon, which I now have lost. But
It's,
I'll tell you. It's a paper by Ken McLaughlin. I don't remember if it's Peter Miller, and then someone else.
oh, I see.
But I'll find the reference here. I think I put it over here maybe. Yeah, I don't know. It's on my computer, so I'll show you maybe later. But there's a good reference for why it actually is a union of intervals, as opposed to, I mean, it's nonsense, yeah.
What do you mean? As opposed to what?
Well, as opposed to, I don't know. I mean, you don't know a priori what the support should be. Maybe it's points for some reason.
Well, the whole development of potential theory, I mean, if you don't want to go into orthogonal polynomials, the whole potential theory is certainly not on the interval. It's an arbitrary compact set.
Sure. And that's part two.
And I didn't catch it when you stated Frostman's theorem, the equilibrium measure, if it's arbitrary compact set, it's kind of a tricky thing, because especially with logarithmic potential, but equilibrium measure always, it's a physical phenomenon. It always supported on the outer boundary component.
Yeah, I mentioned that at least.
Yeah, I kind of didn't, it's, and it's very physical. It's sort of
Yeah, they want to go as far apart as possible.
right. Yeah, and also from the very beginning, I mean, you know it because I know you know it because we talked about it. But if you change this equilibrium problem, but you change the field, like in the disk, your electrons are subject not to logarithmic law, which is not really natural law. The natural physical law is Coulomb law from 3 dimensions, even if you are in 2 dimensions. Because in 2 dimensions, when you take logarithms, you're not talking about particles, you are talking about infinite strings which hit the plane at a point. That's what logarithmic potential is, right? So if you take the natural setting, like you have electrons happened in the disk, and but they're subjected to Coulomb law instead of logarithm with 1 over x, just natural for 3 dimensions, right? Then it's actually an unsolved problem already. It's called Thomson problem because he couldn't figure it out. And what happens with these particles, it's an absolute mystery, because up to the number of 11, if I remember correctly, the particles behave the same way as for logarithmic law, and they equidistributed on the circle.
Yeah, at some point one goes inside, yeah.
Then it goes into the center, and then another almost concentric circle starts forming, but actually when you look at it through the modern computers, which about 15 years ago I did with the physicist in New College, it turns out that it's not a concentric circle. It's looks like a concentric circle, but it only God knows what it is. The only thing we know is what happened when the number of particles go to infinity. In this case, then it becomes the equilibrium measure on the disk, because that means disk is filled with electrons, and it becomes the equilibrium measure on the disk in 3-dimensional space, and it's a radial distribution. It's well known, although physicists can calculate it in a most terrible way with special functions. If you do it through the idea of quadrature domains, you can have a very, very elegant calculation.
Yeah.
But it's a very interesting problem, and I spent a few years until I personally understood that I'm not getting it. What is the pattern, and why? Because these numbers, like why after 11 the next particle jumps into the nobody understands. And you know, there are pictures by now on internet with, I think they can do it with 55,000. That's the last electrons. And the patterns, how like the second curve forms, then the third curve forms, and it starts filling the disk in particular strange pattern. But these numbers, when the electron starts jumping off the previous curve and forming a new curve, there are volumes written about it with absolutely no information, as far as I know. It's a very beautiful.
That's an interesting.
Yeah, it's, if you Google Thomson, it's J.J. Thomson, Lord Thomson. You know, if you Google it, you will, I mean, Zhenya knows a little bit about it because Saf wrote extensively on that problem when he was here in term. But the bottom line is it's for grabs totally.
Okay, so that's interesting. Well, something I wanted to know, at the very end. So the reason I was trying to get to this example, was I wanted to show an interesting dependence. So a cool question I thought to address would be how does rho depend on T0? And in particular, if I take d rho dt, what do I get? So if I take derivative of the T0, of the density with respect to total mass. So in the case of no external field, then it's obviously trivial, it just scales, yeah?
Mm-hmm.
But if you have an external field, it actually does matter it depends non-trivially on the total mass. And the way it depends, this is Genya's result.
From which result?
Genya, Rachmaninoff.
Ah, Zhenya, yeah.
His result. So it depends on it. I'll write Raman measure of the support. But in this particular case, so you'll find that d rho dt in this case is just 1 over pi, 1 over square root t naught minus x squared dx, which is exactly the arcsine law, which is the equilibrium measure in no external field for the interval.
Which is the measure with respect to which Chebyshev polynomials are orthogonal.
The thing is that if you do this for, well, the external field is now Schwartz potential, yeah?
Mm-hmm.
So for nice enough Schwartz potential, up to the critical time, this actually coincides. So this formula coincides with the formula for Laplacian growth. So it actually describes Laplacian growth, which I thought was just an interesting kind of side result. But I always thought that formula was really pretty.
And the equipotential, well, it's kind of the whole classic theory. The equipotential curves are confocal ellipses.
Yeah.
Yeah, it goes back actually to Ivory. It's a theorem of.
Okay. Well, any other questions then? I don't know. I might stop recording if there are no other questions.
No, I just wanted to say that you don't have to. I mean, you know, less is always more.
I'll stop recording.
It's